Hi, welcome back to our second example for 3.4 properties of exponential functions. In this example, we're going to take a look at a graph and then try to determine its equation, which will be in this form, y equals a times b to the exponent x. All right, so there is kind of a nice simple way to do this. Um, we first off, we know that this is an increasing function. So what that means is that our value for b needs to be greater than 1. So we know that. We also know that the function is above the x-axis, so its y value is always positive. So that also tells us that a is going to be a positive value as well. So if you remember from before, we know that a is actually related to the y-intercept, right, in the equation. So here it's a little bit hard to see, but it's probably pretty close to the value of 2. Okay, looking at the graph, because we can see there's 6 here, 3 here. So that's probably 2, and that's probably 1 underneath. So looks like we're at the point, we have the point 0, 2. 0, 2. So that's helpful. And actually, just from that, I know that a should be equal to 2. So that's really helpful. I already know that I have something in the form y equals 2 times b to the x. So what I just need to see next is how are the points changing? So it looks like I have a point here. It looks like 1, 6. And then it looks like there's probably another point right here. That looks like that's at 2, 18. So it's a little bit hard to tell, but I'm just going to summarize this in a table. So I'll take the few points that I have here. So we got 0, 2, 1, 6, 2, 18. If I could get 3, I would. So for 3, I'm not sure where we're at. Looks like about right up here. 54, it looks like. For 3, yeah, it looks like we got 354. So there we go. Okay. All right, so given what I know about exponential functions, I could actually see that there is an exponential pattern here because we have times 3 to get the next term. Okay, that's like that constant ratio. And this would probably hold true in the finite differences as well. If I did want to do a finite differences, I don't think we need to, but 6 minus 2 is 4. 18 minus 6 is going to be 12. And then 54 minus 18, it's going to be 36. So we can see that pattern holds true in the finite differences as well. We have a ratio of times 3. So this constant ratio of 3 is the base of the exponential function. So that's another property of exponential functions. Okay? So therefore, b is equal to 3. So just by looking at the table and the graph, I determined my value for a and b. So just putting it together, we would have a is 2 and b is 3. So you can write it like that. I kind of like to write it like this, 2 times 3 to the exponent. Okay, and if you have another point in the graph, you could always test this, right? You could always check and see. But yeah, that would be our equation for that function. Okay, that's actually it for this example. So I will see you in the next video.